Hello, this is a screencast on the subject of quadratic equations for the Maths for Chemistry content in the module CHE10063. Okay, so quadratic equations, and we're mainly going to be focusing on solving these from a chemistry viewpoint. So just in the same way as we spoke about simultaneous equations. And again, as with simultaneous equations, one of the challenges here is actually going to be putting the equations together in the first place, but we'll get there in a second. Okay, if you want more information on this topic, and in particular, examples in terms of chemistry, then I have linked two QR codes here. This one here is quite useful. It's a very specific website, ChemLibreText, which can be quite useful in other cases, but in particular, this talks you through using the sort of method that we're going to be exploring, these ICE tables that I'll talk about soon. And actually, Elements of Physical Chemistry has several examples in it. Especially some examples applied to acids and bases chemistry that you may have already spotted when you went through the material that I presented on that for the module for this module. Okay, if you are less confident with maths, that's absolutely fine. But I would suggest that you actually go and look at the sort of more basic side of things. So we're talking about sort of solving quadratic equations that are maybe a bit simpler and are less chemistry related first, and then move on to the chemistry examples. And information about that, you know, again, Purple Math is a good website for that kind of thing. Okay. So what do we mean by a quadratic equation? Well, it's an equation that has this kind of form. Y is equal to something times x squared minus something x minus plus or minus 6, okay? Or plus or minus anything. So, you know, we could put a more general form of ax squared plus bx plus c. This example here is for this one. And you can see you've got this kind of parabola, and we have, you know, some positions where the graph intersects the various axes. Okay, so you know you can see here the graph intersects the x-axis twice and the y-axis once. Okay, now figuring out where it intersects the y-axis is relatively straightforward because at that point in time x is equal to 0. So if we put x equals 0 into this equation here, then we end up with y is equal to 0 minus 0 minus 6. So it intersects at minus 6. So that's actually quite an important point about these equations, right? So yeah, that's pretty straightforward. But what about the other way? Where does the graph intersect the x-axis? Well, these 2 points, right? This obviously is a bit trickier because, well, okay, the way of doing it, if we applied the same method, we say 0 is equal to x squared minus 5x minus 6. Well, that's not so easy to solve, is it? Now, there are methods of doing it, but it's certainly more complicated than this one here. Okay. So, as I've sort of alluded to already, there are multiple methods we can use for solving quadratic equations. And some of these work for, simple situations, and others are the ones you need to use when you have a more complicated situation. So the previous equation that I showed on the last graph, you can solve this by factoring. Okay, and you might even be able to solve it by completing the square. I'm not quite sure. I am not going to talk about these two methods today though, because they're not really relevant to chemistry. We never have an example of a quadratic equation in chemistry that you can solve by factoring, because we don't tend to deal in very simple integers. It's very rare that we have a nice easy integer for our mathematics. Okay, we typically have more complicated values with multiple significant figures, and so in that case the only real option is the final one here, which is using the quadratic equation that many of you will have heard of before. So that's a key point, which is that this final option, that's the one we're going to use all the way through. A quadratic equation, for those who are not so sure, for a general quadratic equation as written here, y is equal to this is our general equation, then essentially we can work out x by using this equation here. Okay, so the b's in this equation are that b there, c's are that c there, and the a's are that a there. Okay, and so if we have any one of these equations, we can work out the solutions to it. And notice here the plus minus. That means we have two solutions to every quadratic equation. So I wanted to go through a fairly quick worked example. I'm not going to write on the slides for this one because I've actually animated it turning up, and I'll be able to talk through it quite well anyway. Okay, and this is hopefully relatively straightforward. And as with the previous examples, I'll give you plenty of opportunity to practice. And of course, if you are still having problems, you're very welcome to come to our maths drop-in sessions, or indeed email me about it. So anyway, we have an example here. This is our equation, and you can already see that we've got values of A, B, and C here, and we're going to identify them in a minute, but you can already do it. A is equal to 2, B is equal to 1, and C is equal to -6. So do be careful with those minus signs, and we can put those into this equation here. So don't forget, this is the quadratic equation. So I've written that down. So the first point for using this is, pretty straightforward. We just have to put the numbers in. Okay. Now, the one that people make mistakes on is this one at the beginning here, because this one is minus b. So if b is positive, this value in total will be negative, and likewise if b is negative, then this becomes positive. So do be very careful when you put the numbers into the equation. It might seem a bit straightforward, but just take your time and double check it. Okay, now any number squared is it's going to be a positive value, but nevertheless, it's always worth actually putting in the numbers. So 1 squared minus 4 times 2 times minus 6. And again, this is another classic place where people make mistakes, because obviously, if you don't multiply by -6, this part doesn't become negative, and therefore this whole part with the minus sign 2 doesn't become positive, and you end up with the square root of a negative number, which, as you possibly know already, is not very easy to do. Okay. Nevertheless, on the bottom, it's pretty straightforward, 2 times 2. Next step we do, and we end up with, basically this, because 4 times 2 times 6 is 48, and then we sort out the minus signs. So that ends up being 1 plus 48, and it's -1 out here, and 2 times 2 is obviously 4. Okay, so that's the first bit. Now we could just whack this straight into the calculator, but honestly, you're much better off trying to simplify first. Okay, and even this is a good thing to write down, the simplest version of the equation with the plus or minus still in there. And of course, in this example, we've got the square root of 49, and everyone knows that the square root of 49 is 7. So in this case, we can make it even simpler, but that won't always be the case, obviously. But we can still see we've got this plus or minus. So this means essentially that x is equal to -1 plus 7 divided by 4, all divided by 4, or x is equal to -1 minus 7, all divided by 4. Okay. Another common error would be not putting brackets around here explicitly. Now I don't really need to because I've made the line long here, but if you're not sure, make sure you put the brackets in when you're actually doing the working, because it'll encourage you to put them in your calculator. And obviously if you don't, you end up with -1 plus 7 over 4. Okay, final thing, solve. And yeah, key point, 2 solutions. But nevertheless, we can do this relatively straightforward. -1 plus 7 is 6, divided by 4, 1.5. Equally, -1 minus 7, -8, divided by 4, -2. Yeah, we can do that in our head probably. But obviously, with the chemistry examples, we're not going to get such nice integer numbers. But again, be careful with negatives, because this is where we'll probably end up making mistakes. Okay, so I've talked a lot about the sort of simpler algebraic quadratic equations, and as I already said right at the beginning, the key point when we're starting to apply these in chemistry is actually going to be arriving at the equation in the first place. And the main thing to remember is that when we're solving equilibrium problems, we're often going to end up using quadratic equations. Okay, and the way we can arrive at the quadratic equation correctly, we can use an ICE table, and that's what we've got here. Okay, and I'm going to admit that this slide looks a bit horrific, and I'm just going to say bear with it, and we will go through the example in a minute, which will make things a lot clearer. But nevertheless, I wanted to write out the general example. So for a general equilibrium, we have this to make the point about stoichiometry. Okay. Nevertheless, what we can do, we've got a general equilibrium, and what we've been given in our question, we've been given the initial values of our reactants. Okay, so we've been given the amount we put in the first place, and on that basis, we can make our ICE table. We can say that our initial values of A are the ones we put in, initial value for the concentration of B is the amount we put in. And of course, the initial value for the products is going to be 0 because no equilibrium has occurred. So both of those are 0. Then we start talking about the change. Now, for every A moles of A that have been reacted, B moles of B are going to be reacted, and C moles of C are going to be produced, and D moles of D are going to be produced. So X is the number of moles of these things that have been reacted, and A, B, and C are the stoichiometry. Okay. And then, of course, at equilibrium, it's essentially initial minus change. So in this case, we've got it written out. And again, all the way through, we've got it written out. Okay. And then from that, we can put this into the equilibrium constant. So the point is that for a given equilibrium constant and a given starting composition before equilibrium's hit, we actually can probably get out, all of the other values for this equation. And in particular, we can get out the number of moles, X. Okay, and this equation here looks a bit horrific and certainly could become horrific if you have some very odd stoichiometries in this reaction. But typically, for our simpler examples of acids and bases, for example, A, B, C, and D are all equal to 1, at which point in time this equation is going to become quite straightforward. It's going to become a quadratic because, this is going to end up being x squared on the top, and this is going to end up being x squared on the bottom once you've multiplied out these equations. Okay. If you need some examples of this, or if you want to see some more examples of this being worked through, then there are plenty of these in Elements of Physical Chemistry, and I've linked to both here. So I think there's one example on this one, B2, and there's 2 examples here, and these are both acid-base examples. And this is actually kind of handy in the acid-base ones, and I didn't talk about it when we went through acid-base chemistry before, but this removes, using this table, we actually remove the need for making certain approximations that I mentioned that we were going to make. Like, for example, we made an approximation that our concentration of undissociated acid would be the same as the amount we put in at the beginning. Now, you don't actually have to do this if you use an ICE table. Okay, so it's worth knowing both ways of doing it. Okay, so what I wanted to do for the final part of this screencast is just talk through a worked example. Okay, so this is going to actually look pretty similar to the previous slide, but I just wanted to put some real numbers in. So we've got a real reaction here, and as you can see, this is a nice simple reaction. So only got one product, and we've got stoichiometries of 1 to 1 to 1 to 1, a 1 to 1 to 1. Okay, we've been given initial concentrations of ethene and hydrogen. We haven't got any units, but it doesn't really matter for the purpose of this question. We could just assume these are molar, or indeed their initial partial pressures, which is more likely in the gaseous state. But nevertheless, they are what they are. Our number in the end is going to end up with no units too, isn't it? We've got an equilibrium constant here, and so we can do exactly what I said in the previous slide to find the concentrations of all the species at equilibrium. Okay, so first step of this is always, for any physical chemistry question, and I certainly mentioned this in my acids and bases and redox topics, is writing down the numbers from the equation. Okay, numbers from the question, sorry. So the concentration of ethane, the concentration of hydrogen, and the equilibrium constant. And I've also written down the equilibrium equation here. Now, really important point is we cannot use our initial concentrations in this equation. Okay, people try to do that on my questions for maths every year. Don't do it. You can't. It's not. These are not equilibrium these are not equilibrium concentrations. These are the ones you put in at the start before equilibrium has established. If these were the equilibrium concentrations, then this concentration would be 0. So this just doesn't work. Okay. So don't do that, and do this method that I'm going to talk you through instead. We're going to use an equilibrium table, or an ICE table. I've referred to it as an equilibrium table here just because that's what they do in Elements of Physical Chemistry. And it's still an ICE table because of initial change and equilibrium. Right, write down the initial concentrations of our 2 reactants. So they're written here, so that's pretty straightforward. Write down our initial concentration of products. Of course it's 0 because equilibrium hasn't occurred. The change is, the stoichiometry is 1 to 1 to 1, so it's just a change of x minus x in the case of the 2 reactants, and plus x because 1 mole of this is made for every mole of the reactants that are reacted. And finally, our equilibrium, as before, is the initial concentration minus the change. Okay, so again, we have those written into the table, and 0 plus x is equal to x. Yeah. Okay. So now I just want to show how we can take the information from this table and create it into a quadratic equation that we can then solve. So I'm going to talk you all the way through the process, okay? And you can kind of already see what we're going to do. We're going to take the numbers from the table down here, because these are our equilibrium concentrations, and we're going to put them into this equation here. So this value here, 0.33 minus x, is going to go in place of this concentration of C2H4. This value here, 0.303 minus x, is going to go here, and x is going to go on the top. So that's what we've done here. Okay, now what you have to do is quite a long-winded process, but the first thing we're going to do is multiply the denominator. So this is both things in brackets. We're going to take this and put it up here. Okay, so we can say x is equal to all of that, and then we can multiply out the brackets. And once you multiply these two brackets out, you get this in the middle. And then when you multiply that by 0.98 all the way through, you end up with this. So x is equal to this. And of course, we've still got x on this side. In order for our quadratic equation to be solvable, we have to have, some ax squared plus bx plus c equals 0. So this x needs to come away from this side too. And so we can kind of rewrite this equation here. So basically minus 1x, we've minused 1x from both sides. And so we end up with 0 is equal to 0.98x squared minus, 1.8428 now, plus that number there. Okay, and so we've got our quadratic equation, and we can now use the equation. So we've got a here, b here, c here. And don't forget the b is minus 0.18428, not positive that. Yeah. So let's do that. X is equal to this, so this is our quadratic equation. I've put our number in for b, so it's minus this, so the minus times the minus is a plus, so that becomes positive. Plus or minus the square of, this value here, b, minus 4 times a times c divided by, and that, it's all divided by, 2 times a. Okay, and of course we've got a square root over the middle bit as well. And then all I've done is basically just shown my working effectively here. So we've got, 2 examples here. I've essentially worked out that the bit in the bracket is equal to, which is also square rooted, is equal to 1.65046. Note I've given this to quite a few decimal places. And of course, I would have actually kept the number in my calculator with more decimal places too. So I could have put a ... in here to imply that. But nevertheless, we then have 2 equations. We either have an equation where it's a positive, the plus minus is plus, or we have the equation where the plus minus is negative. So, let's do the plus first. That gives us an answer for x is equal to 1.78. Now, is that possible? Well, no, because 1.78 is bigger than the concentration we started off with of either one of our reactants. So that is impossible because it gives us a negative value for our concentration of our species, at equilibrium, which is ridiculous. Okay, so it can't be this one. So this is a classical thing in chemistry examples, is that one of the answers you get, because we're always going to get 2 answers and we do need to write them down, both of them, but one of the answers we get is going to be more likely than the other, or indeed one of the answers is going to be downright impossible or implausible. Okay, so in this case it's impossible, so we can just say scratch that one out. No chance that one could be that. We'll just put a line through it. Yeah. The other example where our plus minus is equal to minus is essentially this, and it gives us 0.098, and this number is far more sensible because it's smaller than either 0.33 or 0.53. Okay, so it's a sensible number. So that means that then we can work out our concentrations at equilibrium of all of our species. We just basically use these equations here to do that. Yeah. So you end up with 0.23 for our concentration of ethene, 0.43 for H2, and X for our product. Okay. So that's going through a fully worked example of a chemistry problem. Again, I'll give you some opportunity to practice this in the quizzes and beyond that in the tutorials too. If you have any questions, get in touch with me, but otherwise that's that.